this life we live, we are always in a hurry.
I couldn't do business without flying.
It actually makes me physically ill to fly, but I'll risk it because you can't drive there.
Flying always means vacation.
I'm leaving on a safari to Eastern Africa.
I'm a big fan of peanuts.
Once you get into a plane, it's like getting into a time traveling. It's a tube.
So speed is a thing.
But even frequent flyers packed into the belly of a 400-ton metal bird don't really understand how it works.
Rear propulsion and some airlifts and...
I'm pre-med, so you'd think that after all the physics classes I would know something, but
I know it has to do with the wing design.
The gust of air shooting up, I guess. The wind, I think, or coming down. I'm not sure which way.
I would just assume random air currents. I really don't know.
I think the plane goes fast enough to get enough air through the engine.
Propellers make it go up and down.
Jet.
I can't remember. The
propellers.
Wing is fatter at the front and then it streamlines out.
The air lifts it.
Okay, air's always important.
It's pretty impressive that it all works.
Every time I get up there, I think, how in the world is this happening?
He's not the only one. But the secret of flight can be broken down into 4 principles: thrust, lift, weight, and drag. First, we need a forward motion, and that requires thrust. This allows an upward force called lift to get us up in the air and to keep us up there. Overcoming the force of gravity, or weight, and the resistance of the air, a force called drag. To understand these principles, you need to understand the substance we fly in: air. Birds, balloons, and fighter jets all fly in the sea of air we call our atmosphere. Gravity holds the atmosphere to the Earth, the same way it holds you to the ground. Since we live in it and can't see it, it's easy to forget that air has weight and substance, and that it flows and has pressure, just like water does. If you happen to be at sea level, you're carrying around about the weight of a compact car on your shoulders. You don't feel it because you're supported by equal air pressure on all sides. And if you dive to the bottom of a swimming pool, you can feel the pressure increase. Well, it's the same with air. Pressure increases at the bottom because there's more stuff on top. But the light bulb really goes on once you understand how the air and a wing work together.
But then there's a moment that it all comes together, and I think prior to that moment, where you're putting the aspects of flying together, seems the hardest on you at that time. Because you understand this and you understand that, and but then how do they correlate? And then finally, at one moment, you see why at a certain speed, suddenly total lift is possible.
John Travolta's been flying since he was 16.
Off and retracted.
He's logged over 4,000 hours since then and now flies his own Learjet, Gulfstream II, and a Canadian fighter jet back and forth to shooting locations.
Cabins climbing.
He gets asked a lot of questions about how lift works.
People ask me continually, I don't understand how a plane that heavy can get in the air. And then I always tell them to, when they're driving, at least 30 miles an hour, if it's safe to do so, roll down your window, stick your hand out.
This is something that every child has done who has at least thought about lift. When I thrust my hand out the window and turned my hand down like this and deflected some air, it forced my hand up.
The air flows faster over the top of your hand than it does under the bottom, just like it does over a bird or plane wing.
And by cambering it, in other words, giving it a shape of this bird's wing, for example, where you have some curvature in it, you can get even a sensation of more lift.
As the speed of a fluid like air increases, the pressure decreases. And finally, the payoff. The faster moving air over the top of the wing exerts lower pressure, so that the higher pressure air underneath the wing pushes up and gives us lift. For the air to flow faster over the top of the wing, it has to hit the wing at a particular angle. This is angle of attack.
So an airplane's, what we say, operating range, or its angle of attack range in which it makes lift, is actually quite small. It's only about 10 degrees. Whereas 90 degrees is straight up, only about 11% of that, from horizontal to straight up, is actually used.
So there's a thin line between lift and stall.
For example, if an airplane's maneuvered too much, then it becomes nonlinear. In other words, if you pull back further, it doesn't get more lift. It has a stall, and then it does bad things.
Down we go. 40, 50, 60. This is going to be a wild one. 75. Come on, recover.
Pilots are trained to know how to avoid becoming nonlinear. Still, stalls happen. Whether they're studying linear or nonlinear flight, airplane designers examine airfoils, which look like a wing slice, to see how air will flow around them.
Now, actually, the hand is a very poor wing, as you might expect. It's draggy because it's blunt. A perfect airfoil is very round, like this on the front, and sharp, thin on the back, and smooth. So a beautiful wing, like you find on a sailplane or a high-performance airplane, is mainly impressive because of its drag rather than because of its lift. It has very low drag.
Laminar flow, air moving smoothly over a surface, is what the experts dream about. Engineers in the 30s called it streamlining. The term entered the language, and the technique inspired decades of design. Box shapes were banished and curves were in. One of America's preeminent streamliners is Burt Rutan. In stark contrast to the pyramid he lives in, he conjures up planes with curved, flowing lines.
When I'm designing a wing, I think first about what I want to do with the air. If I want an airplane to be very efficient, I take a lot of air and move it just a little bit down. And you do that with a long wing airplane. A short wing airplane, like a fighter that has real short wings, it has to take less air and move it more energetically down. And in doing so, it's not as efficient. It causes more drag.
And walked out of the jungle.
Rutan designed these planes so that you could build one in your garage. A cross between a Wasp and a Star Wars fighter. Rutan named this horizontally challenged plane the Long EZ. Pilots called it a clean ship because it's streamlined. And it doesn't have lots of struts and wires sticking out to cause drag. Another one of Rutan's attempts at turning the world of aviation upside down. Some people actually enjoy this kind of thing.
I like to take off, roll inverted, and fly out to my practice area. It gives me a much better view of everything anyway. And I like to be upside down. It stretches my back out and feels good.
As long as the angle of attack is right, it doesn't matter which surface of the wing is facing up. But aerobatic planes are designed to fly upside down.
The shape of the wing is very specific to an aerobatic airplane in that it's considered symmetrical, so that the airflow is the same whether you're upright or inverted. So you can fly the plane inverted almost in the same attitude with the same nose position as you can when you're upright.
So we've learned how to fly inverted, fly faster, and fly higher, surpassing the birds in the sky. But some still look to nature's flying creatures for inspiration.
I think all pilots are inspired by nature and inspired by birds. And a lot of times when I'm up flying, I'll see a bird sort of circling around a hawk, maybe watching me, or an eagle sometimes. Yeah, and we're all kind of jealous of them too, because they do it so effortlessly.
If you had a cloud's eye view, this is what you would see. Birds capable of reaching speeds over 100 miles an hour. Others navigating halfway around the globe. Soaring effortlessly on the wind for hours. And performing aerobatic maneuvers that would make a fighter pilot's head spin.
They have enormous flexibility. They can put their wings forward or aft or up or down or change. In fact, every feather on a bird may have 10,000 feathers, and every feather is a control surface. Every feather, he can feel the local air on whether it's smooth or turbulent, whether he can lift more there or less, and he can change his shape instantaneously, enormously, in terms of changing the direction of flight. They're much more maneuverable than the best fighter. So a bird really in every way, oh my gosh, look at these wings, in every way is a lot more interesting than a little old fixed wing airplane, isn't he? Oh boy.
Birds serve as living blueprints of the theory of flight. But it wasn't always that way. Nature has taken millions of years to turn them into the flying machines they are today. The architecture of a bird is what makes it such an efficient flyer. Their hollow, buoyant bones combine lightness and strength. Powerful breast muscles drive the stroke of the wing, and these wings do it all, thrusting them forward and creating lift. Thrust comes from the primary feathers at the wingtips, which act almost like propellers. The tips twist up at an angle to the rest of the wing. They bite into the air like the blades of a propeller, pulling the bird forward. At the same time, the rest of the wing provides the lifting surface to stay aloft. But the pioneers of flight were victims of a common misconception: that birds swim across the sky, propelled by a backward and downward wing stroke. We attempted this flapping winged flight, but our wing envy resulted in broken bones and bruised egos. The human body is not designed to fly, but if we were to go back to the drawing board and make some changes, it would take more than just a set of wings. Muscle-powered flight would require big shoulders, really big shoulders, to anchor the muscles necessary to thrust us forward and up. And underneath those muscles, hollowed bones for lightness and a more streamlined shape. It might not be pretty, but it would get us airborne like the birds.
Birds were the motivation for humans flying. They were the symbols, the thing you saw, and certainly have given humans a great craving for flight.
The secrets of lift and drag are older than the first bird. The laws of nature and properties of our atmosphere are the same for a falcon as they are for an F-14. But the lift and thrust combined in nature's design had to be separated in order for humans to fly. The closest we could come to bird flight is soaring, using fixed wings for lift and the Earth's downward pull for thrust.
Without gravity, you couldn't glide. Because that's what's pulling you down, that pulls you far, and then hopefully you catch air, which is being moved up and down by the varying densities and being acted on by gravity, and that's what pushes you back up again. Gravity is the thrust.
Unpowered flight means learning how to use the movement of air. its ripples, currents, and rising columns.
You watch birds in flight, that if they're spiraling up, there's a thermal there, you go over and join the bird. Sometimes the bird will see you spiraling up and it'll come and join you.
You literally feel like you are floating, looking down at the earth. You have a full hemisphere of vision below you, and it's very quiet. There's also just that magic moment when you fling yourself off a cliff and don't die. It's sort of like death and resurrection. And then you land after a flight and you're still alive. It's quite a feeling, it really is.
Every year, the Birdman Rally brings that magic moment to Japan where teams make their own innovative gliders and compete for the longest glide. But gliding still isn't enough. We continue to be obsessed with muscle-powered flight. About 20 years ago, Paul McCready designed a human-powered plane, the Gossamer Albatross. Powered only by the pilot's pedaling, the Albatross flew 22 miles across the English Channel.
Well, everybody somehow wishes they could do human-powered flight. It's an instinct that maybe all humans share one way or another.
The energy needed to drive the propeller and move the Albatross forward was almost more than the pilot could manage. And despite his physical conditioning, he barely made it. The problem is, humans just aren't strong enough.
But when you look at all the numbers, it turns out that to have a plane that is safe enough, stable, structurally sound enough to hold a person, keep a person aloft, be able to climb a bit, it takes about a minimum of 3 horsepower, and that's a factor of 10 more than a person can put out.
So we've come to rely on machines to give us the power to thrust ourselves forward. The rubber band on a toy plane acts as an engine does, providing the energy to move the propellers. Propellers are like a spinning wing. Like a wing, they produce lift, but in a forward direction.
Propellers are airfoils. When they bite into the air and it creates lift and it creates thrust just by the movement going through the air. It's just a big windmill, basically.
So now if we take a piece of air here and we push it aft, it takes a force to do that. And that's the force that's thrust.
Propellers and piston engines have been pushing and pulling planes across the sky for 90 years.
Where I can remember one day looking up and probably the same airplane route that a propeller plane was on was now a jet. And that was captivating. That as a child I was watching technology change in front of my eyes.
So to fly higher and faster, we stopped soaring like the swallows and started squirting like the squid. Creatures like octopus, squid, and jellyfish all work on the same principle as a jet engine: action and reaction.
So the fuel goes into the engine, it's converted into work by speeding up the air, increasing its energy as it goes out the back. And that difference then provides a thrust.
John Travolta's Gulfstream II has 2 Rolls-Royce jet engines, each producing almost 12,000 pounds of thrust. This is an overpowered aircraft.
A plane 30,000 pounds heavier than this plane is run by the same engines. The British aircraft 111, which is an airliner, So you have that level of excess of power. I like overpowered airplanes. They thrill me because in an emergency you have more than you need, and it gives you a sense of well-being at a certain level.
For some pilots, it's more than a sense of well-being.
It's speed is life. The faster that you end up going, there's a lot of things it does for you. One, it gets you through a threat area quicker, and two, it doesn't allow missiles to track you.
Roger that. If somebody's shooting at you, you try to go a little bit faster. Or if you're trying to catch somebody, you try to go a little bit faster. An afterburner is simply a way to get a short what they call dash speed, so that you can get into or out of trouble just as rapidly as possible. Well, an afterburner is really pretty simple. You take an extra piece of pipe and you put it on the back of the airplane, and you dump fuel into it. The fuel ignites and goes zooming out the back. And you get a lot of power for that, but it also costs you a lot of fuel.
What you're trying to do is you're getting enough thrust going out the backside that it equals the amount of weight that you're carrying. So that's when you start hearing ratios where you hear a 1-to-1 ratio is what you'd like to have from a fighter. Well, the F-18 has about a 1.1-to-1 thrust-to-weight ratio.
With that much thrust, a pilot can stand on his tail and for a moment forget about gravity. But just for a moment.
Well, I mentioned to my parents that I wanted to fly when I was about 10 or 11 years old, and they said, well, Patty, you know, women don't become airline pilots, so you can kind of forget that. I was brought up around it, and I remember going out and seeing my dad when I was 4 or 5 years old at the airport, and he'd pull me up into his big airplane and sit me down, and we'd go taxiing around. I always knew that I wanted to fly. I might have 25 maneuvers, doing anything from vertical maneuvers where I'd let the plane slide backwards through its smoke, and that always gets a good reaction from the crowd. Or maybe a torque roll where the plane is rolling going vertical and then sliding backwards through the smoke going vertical straight down. We like to do tumbling maneuvers where the plane's tumbling end over end, and people think the plane's just totally, and it is out of control, so they're right.
National aerobatic champion Patty Wagstaff is anything but out of control. It takes precision and skill to turn cartwheels in the sky. The ability to keep these maneuvers under control is essential to flight. Control surfaces are the movable parts of the wings and tail that allow the pilot to deflect the passing airflow and pivot the plane in the desired direction.
There are 3 axes in an airplane, and the 3 are yaw, which is when the plane goes side to side, and that's controlled by the rudder. Pitch is when the plane goes up and down, and that's controlled by the elevator. And roll is around the longitudinal axis, and that's controlled by the ailerons. When you roll the airplane, you're rolling the airplane around the longitudinal axis. So if you take a string and you put it right down the middle of the airplane, and then you move the ailerons, and you move the wing, you're going to roll the plane around that string. And that's what a roll is.
Patty Wagstaff may be on a roll, but most pilots try to avoid that sort of thing. They want stability.
Most general aviation planes that people are flying around, the pilots have a lot of stability built into those planes. And they're flying around and they put the plane into a dive and they take their hands off, and the plane will oscillate until it returns back to straight and level. Well, my plane and most aerobatic planes are not designed for that. So if I take my hands off the controls, the plane will probably go off into a roll, go into a dive, and stay there. It's not going to want to come out. And that's really good for aerobatics.
The connections between the pilot and the control surfaces in most small planes, even aerobatic ones, is mechanical. Cables, pulleys, and levers do the job.
In a small aerobatic plane like mine, it's very, very simple. It's just push-pull tubes and torque tubes. So when I move the stick to the right, all I'm doing is pulling the tube over and it's deflecting the ailerons. And the same with the elevator. I'm just pushing and pulling tubes that get connected to the control surfaces.
But fighter jets are a different story. The shape of the planes and the giant engines that make them fast also make them temperamental and inherently unstable. Human beings and mechanical connections are just not quick enough to keep these jets under control. So fighter pilots are teamed up with computers in a system called fly-by-wire.
Control is operated, especially like in a jet like this, with a fly-by-wire system, which means computers are trying to help you out, trying to fly the jet as best you can. It's going to get the control surfaces moving to their utmost. Everything is still the same when you're feeling the stick. There's going to be artificial feels that are put in there that allow you to feel the actual control surfaces move. Now, you're moving the stick isn't actually moving the control surfaces. It's just a series of bungees set up to give you that artificial feel. It's very much like the brake system in your car or the steering system.
It may feel like a mechanical connection, but an onboard computer is sending digital instructions to hydraulic activators, which in turn move the various control surfaces. Or you can fly the computer without the plane. Flight simulators have been bestsellers since the coming of the home computer. This one is modeled after the control system of an F-18 jet, but it only hints at the complexity a fighter pilot faces.
Flying a fighter plane is like playing two pianos at the same time because of all the buttons and dials and things you have to work at once just to make the airplane fly and fight. And it takes literally a year to do that, to learn how to fly the airplane and then how to fight the airplane.
Is we've gotten to the point where computers help us out enough that we can have aircraft do things that they were never able to do before. In fact, there's aircraft out there today that cannot be flown unless the computer systems are helping out the pilot do his job.
While a 747 thankfully doesn't do the kind of maneuvers that a fighter jet or aerobatic plane might do, commercial aircraft also use computer systems to move their control surfaces. As passengers on a Boeing 777 watch movies 35,000 feet over Newfoundland, the computers are busy displaying readouts recording every critical function of the airplane and crunching numbers.
Total flying time will be no more than 210, I'm sure.
Even a small corporate jet like John Travolta's Gulfstream II is computerized.
Even with medium range technology, which is what I'm used to, I'll kick off the autopilot and fly an approach on my own just to feel it. You know, I think there's still the urge to be a pilot.
And that's why airplane designers have to take into account human limits in creating their flying machines.
I've been up in several military jets and you know, flown a lot of airlines and handled the controls of 747s and things like that, and they're flying. And especially these military pilots. I think a lot of the small aerobatic pilots, you know, that pull a lot of Gs, it's easy to go, hey, you know, we pull more Gs than you do. But in a military plane, the Gs are sustained.
Pilots call gravity's powerful force on the human body Gs. They are brought on by sudden changes in attitude or speed.
Gs are just the force of gravity, and when we're walking around the Earth and our feet are on the ground, we're being pulled by one force of gravity, one G. When you go up in an airplane or in a car, you experience more Gs. So anybody that's gone around the curve of a car and gets thrown to the outside, those are Gs.
As an airplane moves through a curve, the acceleration creates high G forces that drive the pilot toward the bottom of his chair. High positive Gs drive a pilot's blood away from his brain and toward his feet, causing a blackout. Body conditioning and special gear can help prevent that. No matter how high-tech the plane or well-trained the pilot, things can go wrong.
Well, there are a lot of things that can go wrong. The engine can quit. You can have an engine failure. You can have a propeller failure. You can lose a piece of your propeller. You could have a structural failure. Something could break in the airplane. Those are the main things. You could have a fire. I think that if you experience terror in the airplane, you're not going to be doing your job properly. And I've had emergencies, but you need to just react to those things. You can't be afraid, because then you get frozen with fear.
On a cloudy night in 1992, while flying his family to their vacation home, John Travolta's entire electrical system failed. Landing without a radio and little navigational gear took Travolta back to the way pilots had to do it in the early days of aviation.
On a very rare occasion, you get an electrical failure. And in my situation, there was several consecutive electrical failures. From my early days of learning how to fly, you learn even from being in a single engine plane that if you are in IFR conditions, you find a hole in the sky if you can, and you spiral down through that hole and then proceed to locate an area to land. And in this case, I was able to do that. I found a hole in the sky, spiraled down, and hovered over Washington and landed safely. And the guys from the tower and some other officials came down to shake the hand of the pilot that safely landed the jet at National Airport. And then they found out it was me, and that was even more interesting. But I was very proud of that moment, because I felt that all the years I went to school, it paid off. And even my earliest training paid off, where you learn to fly a plane when you lose everything.
Ever since the first powered flight, designers have tinkered with airfoils, engines, fuels, and materials to coax more speed from their crafts. The problem lies not so much in reaching the speed of sound, somewhere around 760 miles an hour at sea level, but in overcoming the severe punishment an aircraft takes as it approaches that speed. Here's why. Much like the wake of water at the tip of a boat, a plane creates a wave of pressure ahead of it, no matter how slow or fast it flies. When an airplane travels below the speed of sound, the air ahead of it flows out of the way before the plane reaches it. But as an aircraft approaches the speed of sound, it compresses the air in front into a dense shock wave. On the ground, you can hear that shock wave as a sonic boom. Aerodynamic engineers figured out how to slide through shock waves with thinner, streamlined wings and sharper edges that flew more cleanly through the compacted air. But for a supersonic transport like the Concorde, there are even tougher problems. While it takes passengers from New York to London in less than 3.5 hours, the Concorde is considered an economic and environmental failure. At low speed, its streamlined shape doesn't produce much lift, so getting airborne means enormously loud and powerful fuel-guzzling engines. It holds only 1/4 of the passengers and has half the range of a jumbo jet. Engineers are at work on a better alternative to the Concorde, a supersonic that will be more fuel efficient and much quieter. But most important, the next generation supersonic will be able to carry 3 times as many passengers.
The idea behind a high-speed civil transport is to get a supersonic airplane that can, in fact, have the range to go from California to, say, the Pacific Rim in 5 hours, which is a reasonable amount of time. Most people can tolerate 5 hours of sitting in an airplane.
Engineer and pilot Marta Bon Meyer heads a team at the Aeronautics Division of NASA. They're working on better ways to reduce drag. And again, it's all about how air flows.
You've seen commercials on TV, for example, of cars in wind tunnels, and they let smoke out in front of the car, and the smoke runs along the hood of the car, goes up to the cab of the car, and then it kind of billows out. Well, Where it's running along the car and it's staying down inside close to the car, it's in the laminar boundary layer itself, or the layer of air that's flowing along the car.
The boundary layer is the thin layer of air that flows along the surface of an aircraft. Engineers try to make it flow smoothly, avoiding the dirty word of aerodynamics, turbulence. Smooth laminar flow is equal to less drag. Less drag requires less thrust to maintain forward speed. And lower thrust takes less fuel, which means cheaper tickets for you and me. And that makes everybody happy. NASA is trying to come up with a way to create better laminar flow over the wing, thereby reducing drag. And they are doing it with a vacuum cleaner. They are creating suction by fitting the wing with a second skin. It's a kind of glove with about 10 million microscopic holes that suck the air off the wing of an F-16XL.
Suction is being used in this particular experiment to control the boundary layer. What we're attempting to do is take what is potentially turbulent air, and we're trying to suck that back down, suck that bubbly part of it back down inside so that it has a chance to establish itself back on the surface and flow smoothly.
And we're taking data for item 11.
The NASA team thinks they're on the right track. This could translate into savings when the high-speed civil transport takes off.
The potential is that we could actually start designing supersonic airplanes with delta wing planforms, and these airplanes would be 7 to 9% less draggy. The return on that investment is clearly either a longer range airplane, because now you don't have as much drag, you can go further with this airplane, or you can carry more passengers.
Or fly even faster into battle.
Air power gives a third dimension to warfare. Land and sea combat are fought on the surface of the ground. Air combat lets you do this. You can see farther, you can go farther, you can attack your enemy in depth, you can see what the enemy is doing. You can bring the war to your enemy's capital on the very first day.
Author Tom Clancy researches the latest trends in military aircraft for his novels and his nonfiction books.
Let's assume for the moment that you have to go into a battlefield. And you have a choice between being invisible and being fast. What would you rather be?
The military calls it low observables and high survivability. In English, that means if they can't see you, they can't kill you.
Okay, when you talk about stealth technology, what you're trying to do is get an aircraft into an area unseen. The way that you see an aircraft is usually either with a radar or by having some sort of a system that detects electrical signals that that aircraft is putting out.
They call it the black jet. The F-117 is the invisible man of the aviation world. The F-117 penetrated Iraqi air defenses undetected while making precision attacks.
As you see, the airplane is made almost entirely out of flat surfaces. Now, radar is an electromagnetic wave of energy, and when it hits a surface, it bounces off. When it hits a flat surface, it pretty much all bounces off in one direction. Now, in the case of the 117, a wave of energy comes in from the transmitter over here, hits the aircraft, and then bounces in another direction, so nothing returns back to the transmitter. And this guy might as well not even be there. So you have to design the aircraft in such a way that A, it can fly, which is not an easy thing to do with an object made out of flat surfaces, and B, the radar signals that hit it, no matter what direction they come from, are going to go in the wrong direction no matter what.
While the F-117 is all angles, the B-2 stealth bomber is a smooth batwing, but both can slip through enemy air with relative impunity.
Stealth aircraft aren't really terribly fast or terribly maneuverable, but if they're invisible, it doesn't matter.
The ability to take off and land vertically, keeping the maneuverability of a conventional airplane, has long been a desire for the military.
Well, in case somebody rips up your airfields, you have to take off your airplanes from somewhere. which is pretty much why that was invented, or to take fighter aircraft off from ships which are too small to be conventional aircraft carriers.
By using the downward thrust of an engine, the Harrier jump jet can dispense with the need for a runway and take off vertically from the ground. Once it's up in the air, the engine exhausts are swiveled backward, and the wings provide lift in the normal way.
Unfortunately, VSTOL technology has the disadvantage of being very fuel inefficient. It burns up a lot of gas. It is nevertheless a very useful capability. You can deploy the airplanes right up with the troops instead of having to back them off to a runway that's 10,000 feet long.
We would like to show you a picture of the Pentagon's hypersonic spy plane called the Aurora, but they say it doesn't exist. Yet, the rumors persist.
There are probably two very unusual airplanes flying out of Groom Lake, which is a base the Air Force just admitted to exist, although it's been there for an awfully long time. And they're both very, very fast. And one of them's fighter size, and one of them's supposedly quite a bit larger. And beyond that, it's anybody's guess. But there is something, the Air Force, presumably the Air Force, has a couple of very exotic airplanes that they just don't want to talk about.
Or, as one engineer put it,
if I told you, I'd have to kill you. It's a series of compromises flying in close formation. And we like to carry that to its extreme.
It's just a big flying wing, and it's like almost like a bunch of airplanes, 6 airplanes, all flying in close formation.
Although it has a wingspan longer than a Boeing 737, the Pathfinder weighs less than 500 pounds. It's big, but also light, a contradiction in engineering. Paul McCready and Ray Morgan designed this unmanned flying wing to fly very slowly and very high for weeks on end as it studies the Earth's atmosphere. It flew 5 miles high in its first altitude test, and in future flights it will climb even higher into the stratosphere.
There's an interest in having vehicles that can move around in the stratosphere above, say, 30 or 40 or 50,000 feet. The next 50 or 100,000 feet is a mantle, a layer of great importance to the world that in permitting some radiation to come in, screening out other radiation really determines the existence of life on Earth. So you want to be monitoring and doing research that lets you understand what's going on there. This is the layer that protects us.
Cruising in the middle stratosphere requires about 6 times the power and speed needed at sea level.
As we go higher, the density of the air goes down, and the airplane has to fly faster in order to develop the same amount of lift. As we go higher and higher, it takes more and more power to fly. In an internal combustion powered airplane, this is a big penalty, and this limits the altitude they can fly to. The higher it goes, the less power it has.
But the Pathfinder is different. It's powered by the sun.
The more of the surface that I have that I can cover with solar cells, the more power I get, the less surface I have exposed to the air, the less drag I get, and the less structure I have, the less weight I have. It drives you towards something that looks like just a wing.
And when the sun goes down, the Pathfinder will keep going and going and going, running on solar energy stored in its batteries. While others compete for speed records, McCready and Morgan like going slow.
We focus on things that take very little power to fly. The solar plane, for instance, flies on the power generated by about 4 average-sized hair dryers. And we can fly to over 60,000, 70,000 feet on that amount of power. So flying slowly has an advantage, and it reduces the amount of power it takes to fly.
We have made flying machines that hover like hummingbirds, punch holes in the sky, dance ballet, perform disappearing acts, and surf the waves of the atmosphere. For the pilots, the passion is being in the air, whether gliding at 30 miles per hour or slicing through the sky at 3 times the speed of sound.
Flying is sort of something that gives you an infinite challenge and infinite freedom. It's a great feeling.
Flying gives me a chance to just go express myself by myself, do it the way I want to do it, and not have to answer to anybody for it.
It's almost parallel to the feeling I have when I know a character in acting and it's on automatic pilot. I don't have to think about it anymore, I just am it.
I know what fascinates me about flying is the freedom of it. It's just getting away from the ground, looking down, and you're free of all of that. And sometimes when I'm flying, I think this is the only thing in my life that really makes sense.
And if I land on Earth again, I'll be happy just to cut my face.